Hey folks, welcome back again to Advent of Code in F#. We are at day 12 again, and this will be my second attempt at solving the problem. I tried once a couple of hours ago, and I made it way too complicated, I think, for what it has to be. So I'm going to try something else. So this is take 2. Day 12 is hot springs. It's the one with springs and empty spaces and unknowns and some corrupt data where we don't know what it is. And then we have some counts that say how big our groups of springs are. If you want to read the full thing, you can look it up. We are just going to dive right in and try my second attempt. My first attempt, the one I was trying a couple of hours ago, was generating like all the valid combinations because we have to count the number of valid combinations. But it got really complicated really quickly. And I think a different approach is where I just brute force replace question marks with both options and then check whether or not this constraint is okay or whether or not the generated line holds for these numbers. I think that will be way easier than my first only generate valid sequences with a very complicated algorithm. So I'm gonna take it one step at a time, break the problem down into easier parts, and I think we will be done faster. That's my ambition, that is my hope. So let's see here. I already plugged in some things. I already do some parsing. So I parse my input to a list of characters, which is, we don't know what it is. It's an empty space or it's a spring. And we also parse the constraints, so the list of group sizes for springs into a separate data structure. So that's what we're already doing, that's what we have. And that's what we can start from for my second attempt. Second attempt was 2 phases. One, we generate, like brute force, generate all the possibilities for a record, for a line, replacing unknown by springs or empties. And then as a second pass through that collection, we verify whether or not this numeric version of the record holds. And if it doesn't, we can scratch that line. If it holds, we have a valid candidate. And in the end, we will have the number of possible combinations or the number of possible arrangements, for every record. And I think that's enough for part 1. And that's way easier than what I was trying to do. So let's give it a try. Let's generate, as a first step, all possible instances of records where we have unknowns. So where we replace the unknown with a empty space or a spring, and then we can do the rest later. So for this line, we have 10 combinations. So I would like to see more than 10, but I would like to see at least these 10 in the end result. What is happening? So I'm gonna take this example, I'm gonna parse it. There we go. And now let's see how we can generate all combinations for the first part. So that's the characters, sizes. So if we destructure that, we have the characters and we can start playing around with characters. I'm gonna write a function, generate combinations, that takes characters and just like replaces all the unknowns with both options. So that will return many versions of this car list. So it's a list of lists. So it's something like this. We can build a recursive function. Yes, and I don't know how what kind of recursion will happen here, or if we can use like a fold or something. So I'm just gonna start by writing the thing that comes to mind first, which is a that simple recursive function where we pattern match on the characters. If we match on an empty list, so we're generating combinations for an empty list, there's only one possibility, which is the empty list itself. So that's a list of the thing itself. In the other case, we can match on the contents. So it's either a spring or an empty. That's the easy one. So then we just take that as is and we continue. So that's taking, let's do that here. So that's taking the empty thing and doing something recursively. And here that's taking the spring and doing something recursively. And the doing something is literally calling it on the rest of the characters. So that's this, and we can just do the recursive call. There we go. Why is it not happy? Oh yeah, because the return type of the recursive call is a list of lists, and we cannot append a character to a list of lists. We need to actually append this character to all the embedded lists. So that's a map, for example, that says the characters and prepend empty back on the characters again. So that's cool. And in this case, we need to prepend it with spring. So this is doing the thing, but it's not doing the thing for unknown just yet. Why is there a compilation error? Oh yeah, I need to close these parentheses. So this is not exhaustive. We're not doing the unknowns yet. And there's a bigger problem I would like to solve first. It's not tail recursive, so it will work, but it will not be optimal because we are doing a recursive call and then we're doing something with the result. Are we doing something with the result actually? Yeah, we are mapping over it. So we could try to put in some tail recursion here while the function is still fresh and small. So let's try that. So as always, accumulator, once we hit the end state, we can just return the accumulator. When we do the recursive call, we need to do something smarter. What is a something smarter? Actually, I don't know if it's that simple. Yeah, I think it's possible, but we have to think a bit harder, or I would have to think a bit harder about it. So let's not do the tail recursion just yet. There we go. So this is the non-tail recursive variant, which probably will work good enough for our use case. Yeah, let's not overcomplicate things if we don't have to. And things will get a bit more complicated right now because we are going to implement the question mark case, so the unknown case. In that case, we have more than one alternative to consider or to generate. So once we hit unknown, we actually have a spring or an empty, right? I think we could also just implement it this way. So we can like replace this with unknown and do the recursive call and then do this exact same thing, but replace unknown with spring instead of empty, I mean. So I think that actually might work. It's a bit funky because we're doing recursion and then we're replacing something without making the problem smaller per se. We're making it smaller by making an unknown more concrete, but yeah, it's a bit funky in my head, but I think it just might work. It's crazy enough to try. So let's replace this unknown with both things, empty. So this is the replaced by empty case, and then we can just use this character list, I think, to do the recursive call. So yeah, let's maybe take this and put that in there. So this is the case where we pretend it was a an empty spot, and we can do the same where we replace it by a spring. And then we have lots of combinations, and I think we can just smooch those together. There we go. I think that's it, actually. That wasn't too bad if this really was all we needed to do. Let's play around with this a bit. So let's send this to the interactive window, and let's play around with this one example. So we're expecting many more than 10 options, but these 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, these 10 should be in there, at least. We're expecting more. Oh, this will hurt. I was expecting a bit more. I was not expecting 512 options. Whoa. This is giving me pause. How many distinct options do we have? Exactly the same. So, okay, there's no crazy double generation. Yeah, I don't think that's actually possible. We're replacing by two very concrete things. 512 is way more than I thought, but let's continue using this approach because the other way around, that was also pretty hairy. So, okay, we have a lot of options. Let's filter this list to only the valid options. So we can do records. Let's put the destructuring in a lambda, and let's return all combinations. Sure, no, let's maybe keep the original sequence and then all the combinations and the original sizes because we need to filter on that. So yeah, let's do this. This actually still works. I'm gonna do it for my input to make sure that it's tractable. Painful. It's generating lots of combos. Yeah, okay, so it's this might not scale as good as I thought. Oh, actually, it's not the end of the world. Let's put some benchmark on that, or some basic benchmarking. How long does it take to generate all the naive combinations? Oh, there we went. That's a lot of printing going on. Okay, but it's not too bad, right? It's bad, but if this is the amount of time it takes for me to solve today after my first attempt, I would be happy. So this is all the things, but that's too much, and then we can filter on only the relevant things, right? So what would filtering the relevant things look like? We see this whenever we encounter a spring, we know that it has to be a sequence of the next group size. And if something goes wrong, something unexpected happens, we can just short circuit and give up on that option. Okay, we're good to go. So yeah, let's implement that filter. So let's build on all combinations and let's filter. So I'm gonna put everything in a valid combinations variable, and this will filter the things we're doing is we have our cars or combinations and our group sizes, and we need to filter out combos. So let's just filter out all valid combination given the sizes. And this is not a filter, this is a map. Oh, actually we can do this. No, it's a map. So we're mapping over all combinations or all of those things in here. And in the map we filtered this intermediate list So yes, yes, yes. And let's keep sizes in there. We don't need it. No, why would we? We don't need it. We actually don't need characters as well. So forget about this. Forget about this. Forget about this. We don't really care. So yeah. What's the problem here? Let's maybe define this function and figure out what the problem is. Valid combination takes sizes and records or a list of cars, and it returns a boolean. It's a predicate. And we might need some parentheses around this and this. There we go. So yeah, what's my compiler is still not happy? Okay, my compiler suddenly became happy. So yeah, I think this outline of why did I rerun it? Stop. It takes a couple of seconds. So I'm gonna rerun it in the background and we can have a think about this one. So this is actually pretty doable, right? We just take a look at the first size and we try to find the first group we encounter. Oh shit, we broke something. Oh no, that's valid combos. That's returning. Yeah, so this will give a whole different thing. So yeah, nothing is broken. I was overreacting. Let's continue on by implementing this valid combination filter. If we don't have a next group size, we're done. Combination valid. Otherwise. Otherwise, we have a group and potentially some further groups. And then we need for a group or the next group we encounter in characters has to be exactly this size. So let's match on characters. It has to start with a spring. If that's the case, we can actually, it has to start with S springs, right? Yeah, so okay, let's not do that with a pair match. Let's do that with a if cars so we need to have at least this many characters left, and or actually let's match first on the first character. That will help a bit with our algorithm. So match cars with, if it's empty, we can just proceed. So that's a recursive call in our case. Yeah, let's do it with a recursive call. No, is that correct? Yeah, I think it's correct. So a recursive call, we just nibble up the empty, we can forget it exists. I think that is correct. And we just plug in the full sizes again and we continue on with the rest of the characters. So it's not the optimal implementation, or the least CPU cycles, but I think this works. So what happens is, hey, we found a group size we need to do. We take a look at the characters. If the first character is empty, we pretend that it does not exist and we continue on. I think that is sound. If it's unknown, that should never happen. So instead of defining a second type, I'm just gonna crash. So we don't expect these. And there's only one more case, which is we have a spring. Spring appears. So two things need to be true in this case. We need to have not one, but we need to have S springs. So the first S-1 characters have to be a spring in here. And then recursively, all the other group sizes have to be in the remainder of the string. So yeah, I'm gonna just take S minus 1 elements. If S is 1, we should take 0 elements. So yeah, that edge case should be okay here. And these should all be springs, and then the recursive thing should hold. So other springs should all be a spring. So that it should all be a spring. And putting this in a let binding in a variable, so we can just or no, what? Never mind. Yeah. Let's do it. So these should all be springs, and something else should hold, namely the remainder should be a valid combination as well. And the remainder is valid combination, not all sizes, but the following sizes. We just consumed the first group size, and the rest is not CS, the rest is whatever remains after we take the other springs. So that should be this, but a skip instead of a take. What's the problem here? What's the problem here? Let's extract that into a variable so we can take a look at the actual problem. This expression was expected to have a list of car, but it's a sequence of car. I'm dropping into sequence module again for no apparent reason. Bad habit. Let's not do that. It's a bit weird that I'm doing the entire check like this, and the only reason is if this is false, I don't want to do this. It's like a micro optimization. Donald Knuth, or I don't, is it Knuth? I think Donald Knuth would have something to say about that. Is it? I'm gonna look it up. What the hell? Premature optimization is the root of all evil. Who was that? Who said this? To who can we attribute this quote? Knuth, yeah. Little sidebar, sorry. So, it actually works, right? There's a blue squiggly. What is the blue squiggly saying? We are not matching on the empty list case. That would be a bad thing, right? We need to parse a group of size that's at least 1, and we have nothing, so that is false right there. There we go. We have our all combinations. Yep. And now we should have our valid combinations. And there's a type mismatch because my REPL is out of sync. So yeah, I'm gonna rerun everything. Takes a couple of seconds. There we go. Now let's see what our filter does. It crashes hard. So let's take a step back and let's look at the example. Or let's look at this one thing, our characters. So we have this one. And we have our characters. So let's do valid combination. Let's first generate combinations. For cars sizes. For cars, sorry. There we go. And let's now filter these to only the valid ones. given the sizes. Yeah, okay, we crashed just as hard, so let's take a look at the crash. So this is our tiny little test. And there's some name clashes, so yeah, let's just try this. What's actually happening? The input sequence has an insufficient number of elements, and we're trying to do a take. Online, where's the line here? There's some of our code, this is some of our code. Valid combination, line 61. Exactly, this is where we crash. Were we not doing a length check somewhere? I can remember writing length. Did that not survive? Okay, so yeah, this is crashing. We cannot take X elements if the source array does not contain at least X elements. So if we hit that case, that's also a false. Let's just wrap an if around it. So if we don't have enough characters for the take, we have a problem. And otherwise we can look further. Okay, my auto formatter likes it this way, then I like it this way. So if we don't have enough elements in the character array, nope, we're done. Otherwise we can take a look. Are they all strings and is the rest valid? Yeah, I think that might make more sense. So ooh, we're not crashing anymore, people. Do we have 10 though? Do we have 10? We do not have 10. That's a shame. Okay, there's a bug in our valid combinations, probably. Wait. Let's take a step back. How many elements are on this list? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's assume that every one of those is a question mark. And every question mark can be one of two states. It's like 2 to the power of 12. How much is that? Okay, so 512 is a reasonable number. Okay. Then why are we not trimming the search space down to 10? Because there's probably a bug in our valid combination filter. So this is our list. Unknown spring. Yeah, so that's correct parse. And our sizes should be 3 and 2 and 1. Yeah, and 3 should match with this one. So this stays. This cannot be changed, and they have 2 and 1. Where are 2s and 1s? Yeah, okay, there are a lot of options for the 2 and the 1s to follow each other. Yeah, I'm convinced that 10 is the correct answer. I did not misunderstand the assignment, so our program is super buggy. How many question marks do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 to the power of 2 is... Sorry, 2 to the power of 9. Okay, so that's 512. That is exactly our combo's length, right? So that's actually correct. Yeah, that's correct, I think. So the problem is definitely in our valid combination filter. We have 3, 2, 1. Yeah. How can this be 3, 2, 1? Oh. 1, 2, 3. There should be an empty here. This is not correct, but we have 2, 1, then some. Yeah, there's multiple bugs in here. So sizes. It's true. It's not always true, actually. It's only true if there are no more springs in cards. So that's minor bug 1. Yep. So if we end up with no more group sizes, then we better don't have any more springs in there. I would rather say they're all empty, just for that weird edge case where you might have an unknown in there, but it's essentially the same thing. So that was bug number 1. There was not enough filtering going on. And then we have problem number 2. If we just parsed an entire spring cluster, so we parsed S springs, we know something else. We know that the next character, if there is one, it has to be empty. It cannot be a spring, because contiguous, or no, subsequent spring groups, they should not hit each other. There should be some emptiness in between. And currently we're not really checking that. Yeah, so I think everything still holds. Yes, this all holds, this all holds. But here we can do something crazier, as in, if this contains something, it has to be empty. I don't like how complicated this thing is getting. We're like a match within a match within an if, and my brain is telling me to put another if in here. It would work. It will not be maintainable, but I'm not going for maintainable right now. This is my second attempt. Let's first make it work, and then I might make it right. So yeah, I'm just gonna put the edge case in here. So if remainder if it's not empty, then the first thing better be an empty spot. Otherwise, yeah. I'm gonna do the if all springs things first. So if I'm already not liking how deep this is nesting and how complicated this is getting. So if not all our springs, oh dear lord, then we can short circuit with a nope, not a valid combination otherwise, and then this can go. So that was a minor refactoring without running any tests. I'm getting very uncomfortable, but it's my own fault. So then let's take a look at the rest. Everything else is a spring, so this is everything else except after the group, sorry. So then we know if there's an element, it better have a empty space in front. And we can do that with a match, within a match, within an if, within a match. Yeah, why not? So match remainder with we have to see either I'm gonna make it even more tricky. Oh, forgive me, programming gods, for hacking this together and not verifying my work. So what is going through my head? So we are trying to make sure that after we consume a group of springs, the next thing is an empty spot. So we're pattern matching on remainder. And if there's an empty in there, we're good to go. If there's an empty in there, we can do the recursive call. So then we're pretty confident, and we should take a look at everything after that empty spot and the remaining group sizes, which is SS. So that's one case. The other case is where we don't have empty, but we have a spring. Then we also definitely know we have a problem. We just consumed a group of springs of length S, and we encounter another spring. That should be a red flag. Cool. Why is this not happy? The type int. Oh, sizes comes first, sure. And then we have our characters. So just the order of arguments. And there's another, again, this match is complaining. I'm gonna plug it in, but that's like a second time. The smell is getting worse here. I shouldn't have maybe have reused the same union type. Now I'm thinking that should never happen, but now I'm thinking it's still not an exhaustive match. We can have empty. And this list.skip could... What happens if you skip on too many elements? Of course, it also crashes hard. This valid combination function is becoming a beast in a bad way, because this can also crash. So if I use my same short circuity thingy, actually no, if remainder, what is remainder? It's a bad name because I already forgot what it is. It's everything after the group of springs we just parsed. Oh, sorry, we cannot have a problem there. We just took that many elements, so we can just as well skip that many elements. So yeah, no edge case to consider. The only edge case we can have to consider is, what if remainder is empty? Then we're at the end of the string, right? Yeah. So what happens if we're at the end of the string? We better be at the end of our counts. And otherwise, we have a problem. Cool, 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 cool. Or not so cool, because this has become a beast and not as complicated as my first attempt a couple of hours ago, but we're getting there. We definitely are getting there. Let's see how far we get this time. At least that's the correct number. Am I happy with how we got there? I'm happy we have a number. Let's keep it at that. Yeah, not my proudest programming moment. Both on the process of writing this function and on the quality of this function. Like, is it super maintainable? Is it super readable? No on all counts. But first things first, let's see whether or not this works for the example. So we have valid combos, which is a list of all the combos. Yeah, and then we count up all the possible arrangements for everything. So we don't need to know what is what, we can just flat map. And we can just count. "21. 21 is the correct example answer. So let's run that for our input. And these are all tests. Yeah, these are all tests, which I'm getting rid of. If my teammates, if my coaches could see this. It's like a do as I say, not as I do kind of moment. So let's have the computer calculate out all those possible combinations. There we go. Let's now filter all valids and sum them up. There we go. We have a number. Which is the correct answer. Let's first take a look at part 2 and then let's take our cleanup hats. So first things first, let's grab our code and let's put it in a part 2 file. Okay, let's take a quick look at part 2. As you look out at the field of springs, you feel like there are way more springs than the condition records list. When you examine the records, you discover that they were actually folded up this whole time. Uh-oh. To unfold the records, on each row, replace the list of spring conditions with 5 copies of itself. Ooh, my CPU. Okay, so replace the list of spring conditions with 5 copies of itself separated by unknown, and replace the list of contiguous groups of damaged springs with 5 copies of itself. Excuse me? So spring conditions times 5 and contiguous groups of damaged springs with 5 copies of itself. This is getting big. So this becomes this times 5 separated by a question mark. And replace the list of contiguous groups with 5 copies. So we just, okay, we take the group and we copy that by 5. Yeah, that might take a while. What are we saying here? Is it times 5? No, it's more than times 5 in search space, right? Interesting. This makes me think that, do we need to know about all the possible arrangements? How is there only one arrangement? Oh yeah, 1, 1, 3. This is making me pause and like think, do we really need to calculate out all arrangements? Or is there like some clever trick to figure out? Because for one line to have 500,000 arrangements, if we are going to calculate them out, there were like what, 2 to the power of 12 possibilities per record, and we have 1,000 of them in there. Yeah, this might actually be a part 2 that requires a different approach than the first one. Might be. Let's just give it a try for one line, and then we can figure out whether or not we have the patience to do it for my entire input set. So let's try to expand this one. Times 5, times 5. Let's do it. That's not times 5, this. We need to replicate 5 times. And I'm gonna replicate using the parsed stuff, not the string. I'm doing a list map. No, I should just do a parse for a single line. So let's replicate this 5 times. So we need to multiply characters 5 times and sizes 5 times. That's easy, right? And multiplying our sizes 5 times would be just taking the list 5 times and collecting it. Cool. I think we can use a list.replicate. Yeah, we can say take 5 times the sizes, and this gives me 5 times this list, and then we can flatten that with a collect by ID to get a single list. So naive approach, 5 times this list is this. And we can do something similar for characters. So our characters are whatever. Let's take this. So we can play around with this example a bit. So our characters are just empty and spring, and we need to multiply that 5 times, and every time plug in a question mark in between. How do we plug in the question mark? What's the easy way to do that? The easy way to do that is to do this. Replicated cars. Take 5 times the cars, but plug in a question mark. Or take 4 times take 4 times the characters where we prepend a question mark. So that's 4 times the characters with question mark. Wait, what's characters? Empty string. So that should be empty string unknown in front. Unknown empty string, unknown empty string. And we can flatten that. Yeah, so that's 4 times. 1, 2, 3, 4. And the 5th time is just the original list plugged in front. So that's this thing. 1, 2, 3, 4, 5. 1, 2, 3, 4, and a 5th. Yeah, so it's more like this. That's 1, 2, 3, 4, and the original on front. So yeah, I think this is replicating correctly. And we can now replicate yeah, so this should work. Let's grab one line of our input, maybe the first line of the above example, which is something a bit 113. This one. Let's try to run this one. This becomes 3 unknowns, an empty, 3 springs, 4 unknowns, 1, 2, 3. Yeah, okay. Gut check says that it might be okay. 3 springs. Yeah. And we have lots of 113s. Lots of 113s. 1, 2, 3, 4, 5 times. Yeah. So let's run it on this single line, and let's then multiply that by the number of lines in our input. And let's take a look at the length of our input. Where did my files go? Oh, there it is. It's somewhat longer, yeah? Some of them are a bit longer, but not by that much. Okay, so let's run it for one line. So I'm gonna wrap a function around the combo valid thing. Yeah, I'm gonna wrap a function around it. So it takes cars and sizes, it takes a record, and it returns all the valid combos. There we go. Now we can run solve on what do we need? Sorry, we need records in there. Records in there, the parsed records. Yeah, okay. Almost there, almost there. There we go. So we have our records. Let's take the example. And let's run a solve on only the first. Can I take a single element range? Yes, we can. Cool. So these are all the records in the example. This is the first record in the example. And we can expand it or replicate it. Where does that pipe keep coming from? There we go. So this is the replicated first line, and we can try to solve that one. Solve is not defined. I think it is. Should be now. Why is it complaining? Everything is compiling, yeah. Okay, there we go. Oh no. that was that was painful. How long did that take? Timing now on. Okay, let's go. Let's solve one line. 1 second for a line. Damn. How many lines do we have in our inputs? A 1,000. So 1,000 seconds is what, the better part of 20 minutes? Actually, I'm willing to have my computer calculate for 20 minutes. So this is exactly what I'm going to do. I'm gonna map my actual inputs to a replicate. And I'm gonna solve the replicated. And then I'm gonna grab a nice hot tea and come back in a half an hour or so. And we'll see whether or not I get my second star for the day. And if not, so be it. We'll figure out a different approach. Let's go over a quick recap of how we solved part 1 and how I hope to have solved part 2. Maybe while I do that, that should not be this fast. Oh, actually it is. Cool. Cool. So let's run the actual solving. There we go. And let's take a look at our code. What did we do for part 1 and are we trying to do for part 2? We did a naive approach where we generated all possible combinations by just replacing unknowns with either empty and springs and then just combining all those different cases. This was a bit of a weird twist in my head because usually when I do a recursive call, I shrink the inputs, and right now we're kind of shrinking, but not really. The list is not like shrinking by an element, but the first element is becoming like shrunk. Unknown is like this case, and the other two cases are these easier cases, so it's kind of tricky, but it's okay, I guess. Come on, computer. I'm doing too much. I'm recording and I'm running a very intensive algorithm. Oh no, it's really not happy with that. Yeah, okay, we're back. I just killed my process. Yeah, we're back. What did we continue doing? We continued by writing a second step in the algorithm that filters out only valid combinations. And this became a lot more complicated than I thought it would have been. We could like extract some functions, but in essence, this is the algorithm. And I don't know, there's a lot of room for simplification. So where does it get hairy? What's the complicated part? When we encounter a spring, we need to consume exactly the right amount of springs, and we know that the next thing should not be a spring. That's where the subtlety or the complexity of the algorithm started exploding a bit. And on a meta level, I preach taking small steps and writing lots of tests, but for some reason it's just not happening. I can't bring myself to to do TDD or to take smaller steps before verifying my work. So that's something I'm going to take with me for the coming 13 days. Yes, I know it's a good approach. I don't know why I'm having problem doing it. So please hold me to it. If you see me in the coming days, please remind me to take smaller steps and verify my work more often. So yeah, I'm gonna rerun my part 2 solver and I'll be back in half an hour, but I will not have you wait for me. Thanks for watching into the feed. Thanks for joining me. Hope to see you the rest of the Advent for more programming fun. Bye-bye.